Good day, my name is Alexei Ramotar. I'm a medical imaging student in computer science department. Today I'll be presenting diffusion tensor imaging. It's a relatively new technique in MRI. First, I'll give you the very basic principles of DTI, some illustrations of current imaging algorithms that are being used, the application of DTI in health informatics, and finally the original part of the entire research, use of partial differential equations as an alternate technique in imaging. Okay, diffusion in the body is the MRI looks at the water molecule. It irradiates the water molecules. So the water molecules obey a physical concept called Brownian motion. So it's a natural process. The MRI has nothing to do with it. Here I have example. This is a DTI MRI, and this would be a regular MRI image. Let's say the arrows at the bottom here are the field strength of the MRI. In a regular MRI, the field strength across the entire plane is the same. However, in a diffusion tensor image, when you're taking that MRI, you have a gradient. You apply the gradient into positive and then negative. The effect of these two gradients is the net effect would be the same as a single MRI. However, I'll show you why this is important. Okay, imagine this is an axon in the white matter in the human brain. The circles represent water molecules, and the different colors represent the different gradients across the water molecules. So you first set the first phase. So you have a different gradient. However, by the time you apply the second phase, due to Brownian motion, the water molecules move. So when you apply the second phase, the water molecules are totally, the momenta are totally incoherent, and this causes signal loss, which is measured, which is what you measure in MRI. This is the equation used to measure the DTI in MRI. The S is the signal loss due to, in a DTI, whatever signal loss you measure there. S0 is a signal loss in a regular MRI. This entire equation here, except for the D, are parameters that are human-based, that the experimenter puts in. The D is the parameter that we want. To obtain this D, you can see if you log both sides of this, you can get a straight line equation. And the D would be the gradient of that. So you can obtain the D information. In diffusion, there are basically two types of diffusion. One is called isotropic and anisotropic. In isotropic, the signal loss would be equal in all directions. However, what they found in white matter is that the signal loss is not equal in all directions. It's anisotropic. In the image in the middle there, that's anisotropic diffusion on an X, Y, Z plane of our reference. The one to the farthest to the left, to your right, is it's the diffusion. It's the anisotropic diffusion and on the X, Y, Z plane of that particular water molecule. So as you can see, if you can't take the reference just along our reference frame, you'll have to take it along several reference frames because you'll have components in the various directions. So when you take those components, you end up with a tensor matrix. The dxx is basically the signal loss that you obtain from, is the gradient that you obtain in the x plane. Y is in the y plane, z in the z plane, xz is in the 45 to the x and z plane, and so on. This tensor matrix is what's important in DTI. This is the entire purpose of this imaging process. Using this matrix, you can get relative anisotropy, fractional anisotropy, volume ratio values. There are other values you can obtain, and there's lots of research ongoing in this. These values I'll explain to you now how they're important. In this image, Bx, C, Y, and dz, Those are images taken according to the x-plane, y-plane, and z-plane. As you can see, this image was taken using the trace of that tensor matrix. As you can see, the images don't look exactly alike. For example, the image taken according to the y-plane does not look like either of the two, and same thing with the z-plane. The reason for this is because the brightest part of the images in the DTI are those that are parallel to the x-plane, and the dark parts are those perpendicular. So to obtain a full image, you have to incorporate all three images together. And you notice when you incorporate all three images together, you get this dark area, this dark patch. That's called, it's found that when that dark patch is present, that the person who has that MRI done on him is about to suffer a stroke or ischemia. The other function that DTI has is in mapping of the white matter tissue. Using these images were taken using a fractional anisotropy and a color mapping algorithm. And this image, this is a connection between the two halves of the brain, and this is a general 3D model of the white matter tissue. Why is this important? Well, for one thing, DTA in diffusion tensor imaging, it's the only medical imaging process that can detect ischemia in its most acute stage. It's also very important in neurology. It's believed that the white matter, although they're not totally sure, they believe that it's the myelin sheath on white matter that causes the diffusion. It causes the water molecules to diffuse along the white matter. So in Krabbe's disease, cerebral adrenal, that thing, you have these are consistent with myelination, loss of myelination on the axons. So it's very useful to detect again patient to see if a patient is suffering from this. You can compare this against someone with a healthy brain. It's also being used in schizophrenia. There's also been ongoing research in migraines, and it's not just limited to the brain. Actually, you can any part of the spinal tissue you can also look at. There are also current research involved in potential for it to be used in modeling heart, kidney, breast, and muscle. The reason for this, especially the muscles, is that they have the same tensors. The water molecules would diffuse along the muscle paths. So you can basically get the same image out of that. Let's reference. Now, why come up with an alternate method? Well, the problem with a lot of the current algorithms is that they tend to, number one, leave out a lot of information in the tensor. For example, I told you about the trace in the ischemia image. The trace is just the diagonal of the matrix, and they'll forget about the rest of the information. They don't use it. In the line algorithm, the very same thing. If you use fractional anisotropy, you only consider the eigenvalues and the eigenvectors, and you don't use the other parts of the image. What I found out was that in partial differential equations have been used in medical imaging, including in MRIs for image denoising, and also in engineering for contamination tracing and water flow. So these, if you think about it this way, you have a lake, and you drop a dye in that lake, or a contaminant. You can use a PD and measure how that contaminant spreads. But that's an isotropic diffusion, and that's pretty easy to model. It's been done already. What I'm suggesting is that this is the equation, there's a PD that you will be using for this model in particular. The D, that will be replaced by the tensor, by the diffusion tensor that you obtain from the MRI. Using this, you can then model you do the same analogy. You drop a dye in a particular area of the MRI, that's the analogy, and you let it spread. This UT will tell you how it spreads. And from this, you can tell, because, as I said, the water molecules diffuse along the white matter area. It should be diffusing along the white matter areas too. So by this, you can model it. The reason why a lot of the other algorithms they have this ad hoc, they use them, for example, when they come to areas where white matter crosses or their white matter bundles, axon bundles, they start using a lot of ad hoc methods. They just estimate what might happen and then continue. So I think that this method wouldn't be doing that, because although you're using numerical approximation, I think it'll give you a much better approximation than what's currently there. Currently I'm working on this right now. I've managed to implement the algorithms that are already in use. But I'm trying to implement now the diffusion, the PDE, on DTI data sets that I've obtained from this source. I'll also be using finite element method in partial differential equations to do this modeling. It's a modeling method that's used, approximation method. Currently, I'm also working with Professor Jeff Orchard, and we're trying to obtain information from DTI, actual MRI data sets from the University of Western, because they're doing a huge collection. And hopefully, if I can, when I get this implemented on a small image set, I can then try and implement it on a larger image set and compare it against current algorithms, see if we find if it's doing better, if it's faster, and so on. Any questions? Yeah.
As I know that the diffusion is quite slow because it's using kind of iterative way to compute, right?
Yeah.
So what do you think the result and also the performance of diffusion compared to the wavelet?
I think it should be, well, depends on how much the mesh you create, how much you discretize the area of interest. But I think it should, because the diffusion is a lot along the white matter, you can discretize relatively large areas of interest. You don't need to have very small discretization. And I think that would speed up the algorithm. Although you may lose, it loses some amount of precision. But as I said, it's almost brand new. There hasn't been much work done in diffusion on MRI images. So we're hoping to see if it's better than what's currently out there. Although it's almost like reinventing the wheel. Yeah.
You said that they're currently using traces in the one place with their diffusion matrix, I think it was. And
Yeah, the trace of the matrix.
Yeah, and you want to use the entire.
Yeah.
What do you think is going to be the result of it? Like, what kind of extra information do you think that they're neglecting in what they're turning out?
Well, the reason why they use just the trace, or for example, or the eigenvalues, for example, is that they believe, although it's not proven, they believe that most of the diffusion information along the white matter is based on the eigenvalues and eigenvectors. We want to see if probably that is actually true, and at the same time see that if this information, the extra DTI information that are being left out, if it can show you better structure, or if it shows you extra features or something. It's not very sure what it may show yet.
What are you actually seeing in the case of this diffusion? What is occurring?
Okay, when
physiologically.
and I don't put it.
You're saying water molecules,
Yeah.
molecules
Diffuse.
diffusing along the axon sheath or along the muscle fibers. Or
Yeah.
What process is that? I mean, you have the circulatory system in there, but
Yeah.
what are you actually seeing?
Oh, you're actually seeing the water, the signal loss, which should give you the water molecules, and they do diffuse along the white matter or the muscle fibers. So you're actually seeing literally the water, how it diffuses along the white matter or the muscle
What's
tissues.
driving it?
Brownian motion. And
Random
myelin,
motion?
and
It's random.
yeah, it's random, but they believe, as I said, myelin sheath is one of the major reasons. They're not sure, but they believe the myelin sheath that covers the white matter is one of the reasons it diffuses along the white matter, and also the cell structures and so forth. That's
I mean, a question I'll put to you, is, and maybe you can answer it later, is what exactly is happening there? Like, why is water diffusing along there in any preferred direction at all?
no, it's not diffusing in any preferred direction. It goes left or right.
Oh, I see.
But
So
all
it's
you,
just-
yeah.
Oh, okay.
So you're
So
just
it's not in one direction.
yeah,
it's just one plane or other.
one plane exactly.
Oh, okay.
Yeah.
All right. So that makes sense then. I think that's the only other question I've got. Anything else? If not, thank you very much.
Thanks.